Well, here's a diagram of what's happening. Here's Aaron at the beginning, position number 1. In this position, he has some kinetic energy because they tell you that he's already moving. So he has a kinetic energy number 1, which is equal to 1/2 mv1 squared. They gave you v1 in the problem. Now, and that's all he has. In between position 1 and position 2, he's going to go gain kinetic energy because work is being done on him by this force. So the amount of kinetic energy he has at position number 2 is going to be equal to how much he had before plus the additional kinetic energy he got because of the work. And work is force times distance times the cosine of the angle between them. But in this case, the angle is 0, so cosine is 1. So I can just add up the kinetic energy he had before plus how much work was done on him to increase his kinetic energy. The analogy is that the kinetic energy he had before was the cash he had before he came to the mall, and then this is the cash that he earned while working. Now, in this part of it, he's going to go up a hill. As he goes up the hill, some of his kinetic energy is going to be changed into potential energy. So when he gets to the top of the hill, he has less kinetic energy because of the potential energy that he gained. So the amount of kinetic energy in position number 3 is going to be the amount of kinetic energy he had in position number 2 minus the potential energy that he gained. So that's going to be minus mgh, h being this height difference that's talked about in the problem. So that's how much he has in position number 3. Then we come to position number 4. In position number 4, he has some kinetic energy left, and that's what you're supposed to be calculating. That's the answer to this question. Now, he had kinetic energy number 3 in this position here, but in between here and here, friction slowed him down. So friction turns some of his kinetic energy into heat through work. So what we want to do is subtract the amount of energy that the friction turned into heat. So we're going to subtract the work done by friction. And the work is always, oops, I'm supposed to be minus. Work is always the force times the distance. In this case, it's distance number 4. And since the problem gives you the frictional force, you don't have to worry about mu times the normal force. So you're just going to take the kinetic energy from number 3, subtract the frictional force times this distance, and you'll have the final kinetic energy. This part here was meant to be analogous to the smoothies that he bought. See, number of smoothies times cost per smoothie. This part here was supposed to be the socks that he bought because merchandise that you can return is kind of like potential energy.